So my next topic is evolution of Mosfet inverter. So how the Mosfet inverter evolved from your NMOS to CMOS. So before going into the detail of your evolution, so let us first try to symbolize our inverter. Inverter basically a building block of our digital system. So if you know the basic operation and properties of inverter, then the bigger structure like a NAND gate, adder, subtractor and your microprocessor can be easily understood in a better way. So here this symbol basically, if you apply V input, you will be getting some output. If V in is 0, output will be 1. If 1 input V in 1, output will be 0. So here the VTC curve, voltage input output curve, is shown in the figure. Here the transition between the state 1 and 0 occur abruptly at the input voltage half of the maximum supply voltage VDD. So when that is, so when 0 less than V in less than VDD by 2, that is equal to VTH. So then V out equal to 1 or VDD, or VDD by 2 equal to VTH. VTH is the threshold voltage of your inverter, less than VDD, V out equal to 0 volt. For ideal inverter, the output is uniquely determined for all the input voltages except that VDD by 2, and no uncertainty occurs in between. Since the transition between the states abrupt, the dynamic power dissipation is 0. So the performance of a gate as a gate is determined by the following characteristics. So the first one is that the range of voltage that corresponding to the logic level 0 and 1, and the range of input voltage for which the output is undefined. Next one is your third one is switching speed. Fourth one is your static and dynamic power dissipation. Next move on to our VTC curve. Next move on to our VTC curve of your NMOS inverter, that is basically a resistive load NMOS inverter. Here figure shows the basic structure of your resistive load NMOS inverter. So here load represent your resistance. So the input voltage is given to the gate of the NMOS inverter, then output taken from the drain, so that V in equal to VGS and V out equal to VDS. The NMOS is known as a driver transistor here, and source and drain are grounded. source and not drain, source and substrate are grounded because it is our NMOS inverter. So a load is connected between VDD and the drain terminal, so the NMOS, so that the current IL is load current is flowing through it. So the Mosfet is cut off when V in less than VTH. VTH is your threshold voltage and the output is high. But if you increase the V in beyond some VTH value, that will cause the Mosfet to saturate. So the output voltage decreases. So this drop does not occur abruptly but gradually with the finite slope, as shown in the figure from this VTC curve. So there are two critical points in the characteristics VTC curve. If you look at the VTC curve, there are two critical points where the slope is dV out by dV in equal to -1. So dV in by dV out is minus. So from the VTC curve, it is clear that if we increase V in, that means input voltage, the driver transistor starts conducting and the output voltage starts decreasing. So the critical point here, V dV out by dV in equal to -1. So here the low input voltage is denoted by VIL and high input voltage is denoted by VIH, and if the output low voltage is VOL, and when the input voltage is equal to VOH, and here the threshold voltage of this VTC curve is defined as the voltage when the V input equal to V output. This shown by this dotted line. So here VIL and VIH play a vital role in determining the noise margin of a inverter circuit. So the ability of an inverter to interpret the input voltage as a logic 0 or logic 1 depends upon the noise immunity of the inverter. So the noise immunity is very important while designing our inverter. So the external noises have the characteristics of increasing or decreasing the voltage level. When the noise signal passes from the output of the one inverter to the next inverter, the noise may get added to the signal, which may decrease or increase its value. So let us consider that the input of an inverter is 1 to the VIL, and the output is VOH, and it is connected to the another input of an inverter 2. But if the noise is added in such a way that its effect decreases the value of VOH and it becomes less than VIH, then the inverter 2 will not be able to predict its logic level. Similarly, the output of the inverter 2 VOL, the maximum liable voltage to be interpreted as a logic 0 by an inverter 3 is VIL. If the noise increases this value to VOL beyond VIL, it would not be recognized properly. So some figure of merit is there, that is called your noise margin. So the noise margin is very important while designing some electronic circuit. So noise in an electronic circuit is any unwanted signal which may be from power supply or it may be some EM radiation. The noise margin may be defined as the measure of immunity of a logic circuit has to perform in a noisy environment. So that noise, I have told you, that noise may be from your power supply switch or it may be your electromagnetic radiation. So there are two noise margin depending on logic 0 and logic 1. So here low noise margin, in that figure you can see that the low noise margin NML and high noise margin NMH is defined as NML equal to VIL minus VOL and NMH equal to VOH minus VI. So NMH equal to VOH minus VIH. So the significance of this noise margin is that an unwanted signal of amplitude less than Nm will not alter the logic value, the logical value. So the noise amplitude greater than Nm, that is noise margin, result the signal in the transition region and no perfect voltage level will be obtained as a logic level 0 or it may be a logic 1. So your inverter will be confused or any electronic circuit will be confused to predict the logic 0 and logic 1. Here from this figure, the shaded region in the figure show the input and output voltage level. So this noise figure is very important while designing any inverter. Now let us move on to our resistive load inverter. That is basically we move from your evolution from resistive load inverter to our CMOS inverter. Here resistance load inverter is shown in the figure. This consists of a load of resistance are called a pull-up resistor and their pull-down NMOS transistors is there. Because the output voltage is pulled up to VDD by using this resistance R and output voltage is also pulled down through this NMOS. So that's why this NMOS is called your pull down transistor. When V in is less than the threshold voltage, the MOS is off. So V out will be equal to VDD. When V in is greater than VTH, so V out will be equal to 0. So this is the simplest structure of any inverter by using your MOS, and there are disadvantages of this type of NMOS resistive load NMOS inverter. So in the figure it is shown that here we have, it will take resistance R will take a larger space in that area. So large space basically required in silicon substrate to provide a passive component to integrate with your active component. Here active component is your NMOS and passive component is your resistance. So this resistance implementation is very difficult with our active component. So this is the biggest drawback for this type of inverter, this type of resistive load inverter. And also here another disadvantage is that passive, that is your leakage current, that means there will be a huge current flow through the static power dissipation through this resistance R will be high. So to remove that shortcoming, we move on to next type of inverter, that is called your active enhancement load inverter. So active enhancement load inverter, in this case instead of using a resistor R, one NMOS with gate and drain shorted to VDD is used. So here pull-up MOS is always saturated. Here pull-up MOS, because this output voltage is pulled up to VDD by this MOS or this load. So that's why it's called a pull-up MOS, and this lower MOS is called your pull-down MOS. So the pull-up MOS is in always saturation condition, so the V out is not exactly equal to VDD, because there will be voltage drop across this MOS, that is nothing but the threshold voltage of that MOS, that is VTH. For the full swing condition, if the input is in full swing, the output will be equal to VDD minus VTH, that is due to the saturation mode of your pull-up MOSFET. When V in is 0, so the output is not exactly equal to VDD, that is equal to VDD minus VTH. So the two different power supplies are connected, then the gate voltage is controlled so that pull-up MOS will be in linear region, so that V out will be VDD. So this is the next technique we can use by using a two power supply, that is shown in the next figure. Here V input voltage, that means input voltage, gate voltage is controlled by another supply, so that pull-up MOS is not in saturation region, it is in linear region, so that there will be no voltage drop across this MOS. And when V in is in 0, then output voltage V out is fully equal to almost VDD. So there will be no subtraction of with your that is your threshold voltage. So in the previous case, the output voltage swing will be equal to VDD minus VTH. Here in the second figure, VDD V out will be equal to VDD, not VDD minus VTH. So V out will be equal to VDD when V in is 0. So the problem with this type of circuit is two supplies are required. So for a better design, we are trying to reduce the power consumption for a circuit. So here we have used two power supply. That is the disadvantage of this circuit. Two supplies with the two different voltage levels are required. So next evolution of MOS is our CMOS. Here CMOS inverter basically worked in a complementary fashion. Complementary fashion consists of one enhancement type MOSFET NMOS and another enhancement type PMOS transistor operating in a complementary mode. This circuit is in complementary push-pull in the sense that for a high input drive NMOS transistor, the NMOS transistor drives the output node, while the P transistor acts as a load and for low input. So PMOS transistor drives the output node while the NMOS transistor acts as a load. Both the devices contribute equally in the circuit operation characteristics. So CMOS inverter has two important advantages. One is that steady state power dissipation is very negligible. So that is the biggest advantage of your CMOS inverter. And its Vtc curve, a full output voltage swing we are getting from 0 to VDD. That is another advantage of our CMOS inverter. So here in the figure 2 it is shown that the two MOSes are represented by simple nonlinear switches. When Vin is 0, then upper MOS will be on, that means PMOS will be on, that means upper switch will be on and lower switch will be off. So Vout is almost equal to VDD. When Vin is 1, that means upper switch will be off and lower switch will be on. So Vout will be equal to 0. So this will give the full swing of your input voltage, and output voltage will be from 0 to VDD. Next, move on to our VTC curve. So in this figure you have different region, and these regions are denoted by region A, B, C, D and E. So for a region A, Vin less than Vtn. Vtn is nothing but your threshold voltage of your NMOS. So here NMOS will be off, PMOS on. So IDN equal to IDP equal to 0. So Vout equal to VOH equal to VDD, that means high voltage. Next we move on to the region 2. In that region 2, Vin greater than Vtn. Vtn is nothing but threshold voltage of our NMOS. So NMOS will be saturated and output voltage decreases. So NMOS will be saturated, output voltage will be decreasing, and the critical voltage VIL. So the critical voltage VIL and dVout dVin equal to -1 is located within this region. And as the output voltage decreases, PMOS enter into the saturation and it will move to the region C. In that region C, P will move in saturation. In region C, the NMOS saturation, that means VDSN equal to VGSN and VT on VTN equal to VT Vout greater than equal to Vin minus VT on. And if PMOS saturates, VDSN less than equal to VGSP and VTP equal to Vout less than equal to Vin minus VTP. So both these conditions, the device saturation are illustrated graphically in the shaded region. That means in this region both the Mosfet will be in saturation region in the region C. Next, in the region D, Vout less than Vin minus VTP. So this is called your critical point VIH. And next region, region E, when Vin greater than VDD minus VTP, so Vout equal to VOL equal to 0. So that is your last region. So for this VTC curve, we can analyze the operating mode of our NMOS and PMOS. So let's say for your region A, the operating condition for your NMOS will be in cutoff and PMOS will be in linear region. For region B, so NMOS will be in saturation region and for PMOS will be in linear region. For C, region C, both the MOSes are in saturation condition or saturation region. NMOS will be in saturation, PMOS will be in saturation. For region D, your NMOS will move to linear region and PMOS will be still in saturation region. For your E, region E, your NMOS will be still in linear region and PMOS move to your cutoff region. So from this we can conclude that This NMOS and PMOS transistor can be seen as a nearly switches. I have already told you that two MOSes can be treated as a simple switch, and the current drawn from the power supply in both these steady state points A and E region nearly equal to 0. So the only current is your reverse biased or leakage current. And here on-MOS driver can drive any load, interconnect capacitor, fan-out logic gates, either by supplying a current to the load or by sinking the current from the load. So that's all for today's class. Thank you.